I'm Jean-Marc Delhomme. I'm professor of computer science at University of Ivry-Val-d'Essonne, and I shall introduce the committee members of this discussion. Professor Catherine Nielich, from professor in WCS, Electrical Engineering and Computer Science at University of California, Berkeley. And also Associate Laboratory Director for Computing Science at Lawrence Berkeley National Laboratory. Thank you for being with us at a very early hour in California. Professor Michel Daidé, professor at l'ENSTED, and directeur de l'IRIT, l'Institut de Recherche en Informatique de Toulouse. Professeur Jean-Luc Gaudiot, with professor in Electrical Engineering and Computer Science at the University of California, Irvine. Dr. Joe Eaton, technical lead for accelerated graph and data analytics at NVIDIA. And the two supervisors, Professor Naïd Emad, professor in computer science at the University de Versailles-Saint-Quentin, and Professor Serge Petiton, professor in computer science at the University de Lille. You have, Alexander, you have 50 minutes to give a presentation, and then the members of the committee will ask you a few questions.
So good afternoon, everyone. This presentation is about my PhD work on parallel solutions for large-scale eigenvalue problems arising in graph analytics. And let's start straight away with an introduction on graph analytics. So the recent shift in human communications coupled with the technological progress has triggered an extensive growth of data volume. Actually, most of the data of human history has been generated in the past few years. And only 30% of this data is structured in a way that it can be analyzed. That's why formulating the problem is the first step. Out of those 30%, only 1% is being analyzed, which means that even if it's properly structured, there is still challenges to overcome to solve graph analytics problems. So graphs are natural ways to represent relationships between abstract entities, and this is a mathematical structure on which we can run graph analytics, which is the science of analyzing graph structure or the nature of individual components in a graph. Graph analytics problems can be very complicated to solve. Actually, the most advanced ones are NP-hard, and in practice we cannot solve them exactly. So that's why we need some way of approximating the solution and do it with accuracy. So that's where eigenvalue problems arise, because we can formulate graphs as array of data on which we will perform linear algebra operations, and that will be basically matrices and vectors, and then we will be able to solve eigenvalue problems. The third pillar of this thesis is parallel computing and GPU accelerators. So GPUs are graphics processing units. They were initially designed for compute, but for graphics, but very quickly scientists realized that they could be used for compute as well. And that's the last piece of the puzzle, because once we have formulated the eigenvalue problem, it's still very large, and we need all the potential offered by parallel computing and those fast architectures. So here is a real graph and that we are visualizing. So you can see the vertices. You can think of vertices as people, place, or objects that are connected together by some kind of relationship. It could be friendship. It could be roads between two places, and that would model basically social networks or road networks and so on. And here is an example of graph analytics. So this is the exact same graph that we are visualizing here, but what you visualize has been done during this thesis, and the first thing to notice is the vertex diameters that changes. So basically, larger vertices are more important than smaller vertices, and this is done by solving an eigenvalue problem, and in this case it's phase range. The second thing to notice is the edge thickness. So you can see some very bright and thick edges, which indicate strong connectivity between those vertices, and you can also see weaker edges. So at this point, we can almost see and draw conclusion on the sense of the data that we are visualizing. For example, here we see also some color assignments based on spectral modularity clustering into two groups, and that clearly stands out when we visualize the graph into this data. So we can now draw conclusion about the meaning of the graph we had at the beginning. So now how we go from graph to linear algebra? Well, here is a smaller graph for the example, and we will build an adjacency matrix which is simply 1 if there is a connection from node X to node Y, and 0 otherwise. So in practice, graphs are very large and very sparse because each vertex will be connected to a small fraction of the network. If you think of a social network, for example, you might have billions of persons in this network, but you are usually connected to 100 or 200 people. So this will be a very sparse matrix, and that's why when it will come to the compute and the algorithm, we will use sparse matrix representation. So here we use the CSR representation, which is compressed sparse row format, and that basically will allow an optimal compression of the data. And we also choose this format for the work of this thesis because it's widely adapted. So an important thing to know about networks when we represent them as sparse matrices, and what is different from other sparse matrices, is something we call correlate distribution. Actually, they have very different distributions from a vertex to another. And that will create some load balancing issues when we come to correlate computing. The other very important thing to notice is the size of the graph. So here is the real Twitter network that we take, for example, and you can see that we have 1.5 billion edges, which means that in memory it will be about 12 gigabytes. So it will fit on a GPU, but that's still an important data set. And to be more precise on the polar distribution and the load imbalance that we have an average degree, so an average size of row that is 35, but a standard deviation that is 10 times this average. And what it means that there are some vertices with 3 million edges, and some half of the data set has actually less than 5 edges. So we will need special algorithms to handle that, like the regular sparse linear algebra that we use for PDE's equation or this type of thing cannot work in this case. So eigenvalue problem. An eigenvalue problem is about solving AV equal lambda V, where A is a matrix, V will be called the eigenvector, and lambda is the eigenvalue. So basically what it means is that the eigenvector V doesn't change when the transformation A is applied to it with this lambda factor. This has application in many fields, but here we will focus on graph analytics, and in graph analytics, eigenvalues will give key information on the structure of the graph. So for example, we can use them for ranking and clustering, and this is what we will do in this case. Also, there are a lot of different types of eigensolvers. It's not like we have one eigensolver that can solve everything. So in this case, since we have very sparse matrices and we cannot afford any filling in the matrix, so we don't want to change the sparse pattern because that would dramatically increase the memory requirement, we will use Krylov method. And Krylov method has the nice advantage that they can preserve the sparse pattern, they don't add any value in the matrix, And also, they compute the dominant eigenvectors by nature, which is exactly what we need in the case for network. For PageRank, we need the largest eigenvector, and for clustering, in the case of modularity, we will have a subset of the smallest of the largest eigenvector. So now the third big part of this thesis is about GPUs, and to better define the GPU architecture, let's first have a look at this schema of the CPU architecture. So what you can see here is that we have arithmetic unit in green, so we have 4 of them in this case. It's a regular quad-core CPU, and we have a huge console and a huge cache. So this is very good at doing latency-oriented workloads, and since there are large caches and sophisticated control, by sophisticated control I mean we have range prediction or prefetching, and that will be very good at handling sequential job quickly and naive sequential code and making run very fast. Whereas the GPU is completely different. So what we see here is that we have many more cores. It's 5,000 cores in a GPU nowadays for the most powerful one. The control is distributed per each stream processor, and we have also smaller caches that we will manage manually. Another very important point to know in our research is that the GPU bandwidth, the memory bandwidth, is much higher than the CPU one. It's 3x to 4x faster. And this is important because eigenvalue solvers are memory bound, so we hope to benefit from the faster bandwidth in the GPU. And now let me present the agenda of the contribution of this. So we will start with spectral modularity clustering, which finds communities in social networks or in other type of networks, basically community detection. Then we'll see a new algorithm for computing similarity weight on the edges, and this is done with Jacquard similarity and PageRank. Then we have multiple implicitly resorted Arnoldi method on GPU, which is the Arnoldi method with auto-tuning of the subspace size, and we will see that in the context of PageRank applications or ranking. And we have the same auto-tuning for the subspace size, that's in length of method, and application in clustering. And finally, conclusion and perspective. So, spectral modularity clustering. Here is the graph that we saw at the beginning, and I didn't mention what it was actually, but here vertices are groups about US politics, and edges represent frequent copper phasing between those groups. So if you are Amazon, what you would like to do with this data is basically build this feature that they have, which goes as people who bought this item also bought that other items. And when we run the clustering, here is what we found. So we can clearly detect those 3 clusters which correspond to most famous politics current in US politics. So how does the modularity work? Well, we have first a matrix that we want to form, which is B here and called the modularity matrix. And this is simply the difference between the adjacency matrix and what we would expect randomly. So when we compute the modularity quantity, here with this formula, where X are cluster assignments, the larger this score is, the more good we are at finding clusters. That's because we would expect more connection into our cluster assignment than what we would have randomly in a graph. So, as you can guess, it becomes a maximization problem, and that's what we'd like to solve. So, finding the optimal solution for that is very expensive, but thanks to the current Fichet theorem, we know that a good approximation of this optimization problem are actually the dominant eigenvector of the matrix B. And matrix B here, which is dense in the way we formulated it earlier, but it's also rank 1 update of a sparse matrix. So we will operate on the sparse matrix and just update the results. And it's symmetric also, which is why we will be able to use nexus. And finally, at this point you may wonder, okay, we solved this eigenvalue problem and now we have eigenvectors, but how does this relate to clustering? Because what I want in the end as answer is in each cluster belongs each vertex. And that's why we will have to come back from the real values of the eigenvectors into discrete cluster assignments, like cluster 1, cluster 2, and so on. And this is done with scaling clustering. We simply see the eigenvectors are multiple dimensional points, and we cluster those points. So here is an overview of the teaching, just to make sure it's clear. So we form the modularity matrix, then we solve the eigen problem, and then we cluster the eigenvectors, and finally we have our clusters assignment. So now I would like to add a few words about the eigenvalue problem. So we solve here v equal lambda v for multiple v, and we will look for the largest eigencurves. Usually we will compute as many eigencurves as we want clusters, but we also show that we could compute actually less eigencurves and still compute a larger number of clusters, which is very relevant because we can reduce the computational cost. And we can do that and still have a good approximation of the clustering. So because of the matrix, the property of the matrix B, we can use the length method, and in particular we use the implicitly restarted length method, which has the nice advantage that it imitates the memory requirements. And it goes like this. So first, we have to choose a subspace size, which is very important because of in the rest of the presentation about eigensolver, we will talk about auto-tuning of the subspace size. Then we iterate, so we will compute factorization of the matrix. Basically, the idea behind that is that the small matrix resulting of this factorization will have the same eigenvalues and the dominant eigenvalues of the matrix, of the D matrix here. So that will be an approximation of the problem we are trying to solve. Then we solve the problem into the subspace, which means we compute the eigenvalue of the small matrix. We estimate the residual. So, and then if we are close enough to the quality of the result we want, we stop here. And otherwise, we just restart and concentrate the information of interest into a smaller matrix and redo the factorization and solve the problem into the subspace, and so on until we have the approximation we want. So, at this point, it is important to know where the time is spent. And in this whole application of clustering, the eigensolver takes 90% of the time. So, it is actually good news because we know exactly what we need to look at in order to have better performances. Also, this is a profile on GPU. We implemented it directly in GPU. So scaling here doesn't take much time. It's in the small 10% fraction, but it might take more time on CPU. So now, what takes time in the eigensolver? That's sparse matrix vector multiplication. Because when we do the length of factorization, we run a lot of SPMG. And that is also 90% of the time of the eigensolver. All of the rest of basic linear algebra operations don't take much time. And in this thesis, we don't focus much on optimizing the SPMG. We assume that, so basically we took a very good, very optimized SPMG for our problem, which provides perfect load balancing, which is very important for graphs. And we run that on GPU, and it ran at 60 to 70% of peak performance of the memory bandwidth. So that's just what we use as building block. And then we will focus on reducing the number of SPMD, since now we are confident that we have a very optimized SPMD, so we just want to reduce the number of SPMD to be faster. Here is a quantitative result about this approach. On the right, this is the ground truth clustering. That means that someone read the title of the book and the abstract and assigned categories to this book. On the left, this is what our algorithm found. And when you think about it, our algorithm doesn't know about what the data is. It could be social networks for our algorithm or anything else. We are just analyzing the topology information, and we are still able to discover we are still able to discover something that is meaningful in terms of data. So, a quick word about performances now. First, we selected relevant and real networks for our application. You can see that the largest one has 100 million edges. And on these networks, I would like to highlight that we are able to cluster it in less than 1 second. That means near real time for all the graphs below, with 1 million of vertices, for example, and 20 million of edges. So here is how it compares to the agglomerative scheme. So for the agglomerative scheme, we selected recent works on modularity maximization. So it's not spectral, it's based on aggregating vertices together recursively. And this is from George Karitis, which is the author of the well-known Metis partitioner. So we can assume it's pretty state-of-the-art. This is work from 2015, and the CPU results were on dual socket in Intel. Here we compare one GPU against the dual socket, and we can see that we have around 3x speedup in average, and up to 5x speedup. So this is the first goal we were trying to achieve, because data analytics is often very time critical. So the first thing was to make it faster. The second thing that is important to notice is that we have some quality loss. That is because spectral clustering is a global scheme that is trying to see things that are visible at the highest level. And this is not always true. Sometimes the bottom-up approach is better at finding relevant information based on what's happening locally. So this is why they don't always perform the same on different networks. That's the observation about this work and a quick summary of the contribution. So modularity maximization was an existing technique that we improved by identifying multiple clusters at once and also supporting weighted graphs, so not only the sparsity pattern but also existing weight in the graph. We can detect the number of natural clusters by keeping the number of eigenvalue constant and varying the number of k-mean clusters in order to just pick the best clustering score. And we also have speed up to 5 to 8x on GPU. So I showed the result for 5x. For 8x, it's comparing against another GPU work on agglomerative scheme. And what to do next now? So we have trade-off of speed versus quality. So first we would like to improve the quality of the spectral clustering to make it better. And then we also see that we spend less time in the SMG, so we want to reduce the number of SMG. And those two things, they are the next sections actually. So they were developed during the thesis. And we can also think of parallel local refinement, which is also done in many clustering frameworks, and k-means improvement in order to not run many different k-means, but maybe just have a k-mean algorithm that detects the number of network clusters directly. So now Jacquard and similarity weight. So Jacquard was initially defined between two sets. It's a similarity measure where we So yeah, Jacquard is defined as the intersection of two sets divided by their union. So the higher this score is, the more similar the two sets are. So how does it apply to graph? Well, it's straightforward. We just take the neighborhood of two vertices that are connected together. We intersect this neighborhood, and if they have a big intersection and a small union, that means they are similar, assuming that similar vertices have similar neighborhoods. This is what we do for graphs, and in Jacquard, this is done by using cardinality. So we just count the number of neighbors and get the cardinality of that. In this thesis, we add weight. So we'll see later that it will be weight related to the importance. And also an important thing to know is that I mentioned intersection. This is what is going to be very expensive in terms of computation. It's close to a matrix-matrix multiplying in terms of complexity. We can actually do it by solving a force matrix and force matrix multiply. Here we solve it with binary search, and number affinity parallel, we just intersect all those sets at the same time. And for the union, we can infer it from the intersection. We don't really have to compute it, it's linear time. And here is how it would look on this graph. So if we take this simple graph on the left, we compute the Jacquard weight, which are here, and then we can see that we have this thickness notions here. So the vertex at the center are strongly connected, where the one on the periphery are not that much connected. This is useful as is, because as we can see here, or we can also use it in graph matching or agglomerative aggregation in multi-grid problems. And because we want to aggregate vertex that has similar neighborhood in this case. And what we want to do in our case is to use them in the clustering scheme. Because remember that we have a global clustering scheme, and having this type of information from the beginning will provide some local insight, and our hope is that it will impact the spectral clustering scheme in a good way in the end, by providing local insight. Now, I mentioned we will also have vertex weights, and those vertex weights are based on PageRank. So PageRank is an important measure, or a ranking measure. It was invented by Larry Page, the founder of Google, and this is based on how influence propagates into the network, based on topology, and that will give you a ranking score that we later use in our Jacquard similarity measure. In terms of math and how we compute it, a common way of doing it is by solving an eigenvalue problem, where we look for the largest eigenpair of eigenvector, to be precise, because we know that the largest eigenvalue is 1, because of the way the matrix is formed, because it's a Markov chain. And so since it's a Markov chain, it's substochastic, and we know that the largest eigenvalue is 1. And we will form it this way by modeling, adding some model about the random web surfer and so on. So in the end, we don't really form it because it will be dense. But what we see is that it's a rank 1 updated matrix of the Markov chain with some dot product and constant information. So by using a simple method to solve this, that would be the power method. And this method simply run a force matrix vector multiplication, normalize it, and the output of this operation is the input of the next iteration, and so on. And it will convert to the eigenvectors we are looking for. And here is our result. So it's always the same graph. Here it's also the result that we saw earlier, but at this point we don't have the cluster assignment. But we can clearly see that here we had no information about what is important and what connections are important. And at this point we can clearly see those two clusters. So now let's see if it improves our modularity clustering. So just to summarize how we do it, we have the PageRank first, then similarity, we compute the edge weight. Now we have a weighted adjacency matrix that we will use in the spectral modularity pipeline that I showed earlier. And in the end, we have the community detection, and hope that this result is better. And this is actually true. So in NVGraph, which is the library in which the clustering was implemented, the spectral clustering was implemented, we have up to 80% improvement on spectral modularity. And we were also curious about how this would work in existing state-of-the-art partitioner, and we also tried to feed the Metis partitioning software with the dry-card weight. And we actually found 10 to 15% improvement. So that's it. So for the contribution, this approach is new, and it's a new similarity measure. We account for vertex weight, which can be computed by PageRank, and we have RL implementation that is 10 times faster on GPU than on CPU. And we also improve the clustering by 15% in Metis and 80% in spectral clustering. So now a few words about the Arnoldi method for PageRank. So I mentioned one way of computing the PageRank was the power method. Actually, the idea of Arnoldi, so just let me give you first the speed up of the power iteration method. So here we compare the power iteration method on CPU versus GPU. So we still have the same network here, and we compare one CPU, a consumer one, against one CPU, the same one, with a Titan X. So the idea is that in the past, let's say you had this machine without GPU, and now you add a GPU, and this is what the speed that you will get for running basically power iteration, which is basically SPNG in a loop. So, and we have we have 10x speed up in average, and up to very high speed up when we are better at handling load balancing on those data sets. So we are comparing against Intel NGL and old thread, so the parallel version implementation. So now for Arnoldi, we think we can do better because we will keep more information. We will store all the at each iteration, we will store the output of our SPMD in some way that we can use it later and grow better understanding of what's going on with the convergence. So we choose the subspace size as for Lanczos, then we compute a factorization, similar as the Lanczos method that I showed earlier. Instead, here we have a small matrix. The subspace will be slightly different because it's a Hessenberg matrix, while in Lanczos it was 3 diagonal. Then we solve the problem in the subspace again. We compute the residual and restart if we haven't converged. Now, one of the problems is when we choose the subspace size. So as you can see here, without reorthogonalization, we might not converge, and actually using a larger subspace will not be very helpful. And you can see that the subspace size of 6 here, that's better than a subspace size of 12. So we would like to relax the choice of the subspace size by having some auto-tuning of the subspace size, and this is what was done in 2015 for MyRAMNS, for the adaptive selection of the subspace size. So in this thesis, we changed it a little bit. So in the past, we had to say which subspace we were interested in, and now we have a frequency that we can use, so we just select the minimum and maximum sizes, and we will automatically generate the subspace sizes. And then we will evaluate the quality of each subspace size, and we just take the best one for the restart and discard the others. We assume that a subspace is better if its residual is smaller. And we do that till we are satisfied with our approximation. Now, in terms of GPU implementation, as you can imagine, we operate on 2 very different order of magnitude here, because all those source matrix vector multiplication are very large, and they are on the big graph matrix. While what happens in the subspace size is very small. In the case of PageRank, the subspace can be 4 or up to 10, depending on the parameters. And In clustering, that will depend on the cluster we are looking for, but we don't expect it to be larger than 20 or 30 in practice. So that means when we will compute the eigenvalues of the small subspace matrix, we will want to use the latency-oriented architecture, which is the CPU. So in the end, we have this sort of hybrid parallelism. So the factorization will be done on the GPU, all the SPNGs are done there, and we form all our Hessenberg matrices. And notice that we can do some overlapping here, because when we will actually compute the eigenvalue of the first nested subspace, we can continue to compute the factorization on the GPU for the next nested subspace, till we reach the largest subspace size. Finally, when we do the restart, we concentrate the eigen information into a smaller subspace, and we do maybe the factorization if we haven't converged, and if we converge, we just compute the eigenvectors. So, just to summarize the performance that we had, that is for the PageRank application. So we started with our GPU power iteration, which was 10 times faster on GPU than one CPU. Then we used the implicitly restarted Arnold-B method on GPU, which is up to 15x faster. And this is up to, but in average for PageRank it would be more around 4x with standard parameter. The up to 15x is when the eigenvalue are clustered and the problem is hard or takes more time to converge. And we have an additional 8x speedup when we use auto-tuning of the subspace size. And this is how it would look. So we convert Arnold-B without auto-tuning, and here it's with auto-tuning. You can see that the blue diamond shape here represents the subspace, the size that we select. And we do an active switch of the subspace size, which follow the green curve to converge much faster after 10 restart cycle, while IRAM is probably losing some orthogonality here or having issues to converge and take about 3 times more cycles to converge. And the last section is about implicitly restarted Lanczos with auto-tuning. So the idea is similar to the Arnold-B method, but it's just it was not done in the past. So the auto-tuning was of the subspace size. This one is new for Lanczos. And we start with the same idea. So instead of computing the Hessenberg matrix, we'll have our 3 diagonal matrices here. And in the same way, a subspace will be better if its residual is smaller. So this is the same as for the Arnold-B method. And now what we are curious about is how this improves the clustering. So we can see that we have a 2.3x speedup. This is speedup directly related by the reduction of number of sparse matrix vector multiplication. And we also have something else that is very interesting, is that in the past, the majority maximization algorithm used to require 64 bits, or not really require, but we often had better results in 64 bits because it converged faster. While now, with using the adaptive subspace size, we were able to use 32 bits in some cases that used to require 64 bits. And that's simply because we just select best subspace at each cycle. Again, now we found the clustering in 0.2 seconds for our Hollywood graph. So that's almost in real time for this one. And again, it's still the same. Oh, that's actually important. You may wonder what is the cost of all those transfers between CPU and GPUs. And since we have multiple subspace and we will compute the eigenvalue of multiple matrices, how does this impact the performance when we compare the two methods, or the method without auto-tuning and the one with auto-tuning? And it actually it's not even visible on a profile because the graph is so large. We are talking about hundreds of millions here of edges, while the small subspace, as I mentioned, are like 4x4 matrices or 10x10 matrices, and we can overlap that. So it's basically less than 1% of the time, the cost of the auto-tuning. Here is the similar plot for Lanxos. So we can see that we also do active switch between the subspace size. At the beginning, it's not clearly better. That's because we measure it just after the result. So sometimes it creates small spikes. But for long term, we can see that here the regular Lanxos start to stagnate, which is very common in Krylov method, while the auto-tuned version at some point found a very good subspace that has the eigenvalue we are looking for, and we reach the precision we want much faster. And for this example, for instance, the number of eigenvalue we are looking at is 7, and subspace size is 22, and this is on our largest data set. That's what I have. So now conclusion and perspectives. Just a quick summary of the contribution. So we have new algorithm and improvement of existing techniques. We also have GPU implementation for everything, and those GPU implementation are faster than what we compared against. And we also have improvement of eigenvalue solver. So for Lanxos, we added auto-tuning of the subspace size on GPU. And for MyRAM-NF, we implemented it on GPU, and we also changed a little bit the way the subspace are generated. As perspective, there are a couple of them that are very technical, but the big thing that I would do if I had more time is first train 16 bits. There are a few reasons for that. First, that's because we noticed we could reduce the precision by using auto-tuning of the subspace size. So, the second reason is that GPU architecture is evolving toward having great performance in 16 bits and special circuits for that. So I'm very curious about the result that it could be for graph analytics, because we could have, it could have two benefits. The first one would be to make larger graphs fit into the memory of one GPU, because it would require less memory, and we will also use less bandwidth, so we would expect it to be faster. And the second important thing, I think, is to try the similarity weight that we develop into other applications than clustering. It's not limited to clustering. It can be useful maybe to find SAS or any other application that you have in mind. I'm also curious about the result that you could use in AMG or this type of methods. And also the weights are not, doesn't have to be PageRank. It can be other weights. It could be cost of vertices in the case of the book, for example, or there are many options. We would like to do also more further analysis of the subspace size selection. It could be done by doing more experiments, and there are so many parameters in Krylov method that we can play with and adjust that I'm sure we can even get better performance by doing more analysis and trying more stuff. And finally, multi-GPU implementation. So this work is single GPU, but as you saw, we can still handle very large data set, and we run on thousands of cores. But multi-GPU would be quite reasonable to do here, because the most important part is the eigensolver, and we have very good distributed eigensolver existing already, so that should be reasonable to do, and the rest, like for Jacquard, it's embarrassing with RL, so it's just about distributing the data and running on multiple nodes. So that's it. That's a summary of the publication. So you got 5 publications. One of them is not submitted yet, and 2 of them are directly on the eigensolvers, and one on Jacquard and one on modularity clustering. That's it. Cassie, can you hear us?
You know, I can hear you, but I can't hear, I wasn't sure if there was a question for me.
Yeah, because I don't have a microphone, I think.
Oh, you can hear me, but not the question, right?
Right.
Okay.
So it's just an invitation for you to start asking questions and making comments.
Okay. Well, okay, so I'll start. First of all, it was very nice. There's a lot of great work in here, and I think it was very well presented both in the thesis and here in the presentation. So thank you very much. It was quite interesting, and I've learned something about some of these algorithms. I did have a question about kind of the analysis relative to the best possible possible performance on both of the machine types, both CPUs and GPUs, because most of your performance, a lot of your performance comparisons are between a GPU and a CPU. So the question is, do you have any confidence that either one of those codes is running as fast as possible?
Yes. Yes. So basically, SPMV is the most important operation, clearly, in everything that I presented. And we know that the GPU bandwidth is higher than the CPU bandwidth. And we also know that on GPU, the SPMV is running at about 65% of peak performance. So by doing the math, we can expect 2 to 3x mechanical speedup by comparing similar GPU and CPU in terms of price. And yeah, that would be my answer.
But for example, you have some speedups that are 10x.
Yes.
So that exceeds
exactly.
the theoretical limit. So that means that the CPU code is usually running much below its theoretical.
Yes, absolutely. So in the experiment, you're I suppose you're talking about the comparison against power iteration, which is this one, where we have this 10x average speedup. So that is because in this case we don't compare to a dual socket CPU. Also, so it's really the GPU is clearly more powerful. So that's also why the speedup is higher in this case. That's the only experiment that is like this, and that was to show that when you have a given machine with one CPU, that would be the speedup you would get if you add only one GPU into your machine. So it's not like limited. It's like the memory type of reasoning is not working here because we don't have the same power in the GPU than in the CPU. So, but even if we had 2 CPU, we would still be around 5x. And that, I suppose, is because in the MKL, I guess they are more optimized for PD equation and more regular work in parallel, while those graphs are very irregular, and in our case also, we have very well-balanced force matrix vector multiply.
Okay, yeah, I think that trying to understand why the CPU performance is lower than expected, whereas the GPU performance is closer to what the maximum is sort of the interesting question.
In practice, we would expect higher performance for CPUs because they will be better for the random accesses. Because we will have, hopefully, must use variable of the dense vector into cache, and we would access them faster. That's actually why when the GPU bandwidth gap is 3 to 4x, we have a speedup of 2 to 3x on GPU versus comparable hardware.
There's also a scale issue here that these are very large graphs relative to what fits in cache, right? These do not fit in cache, so you don't get the expected caching benefits on the CPU.
Absolutely.
Right, so the question was, for example, if you're only using one word out of a cache line because of the fact the graph is sitting in main memory, and you're not using the full cache line, then that would explain why you may be saturating your memory bandwidth in the few, but not seeing anywhere close to kind of the theoretical peak bandwidth, because you're actually effectively only using, say, a quarter of the bandwidth.
Absolutely. Yes.
Okay. That's all my questions.
Thank you very much. Now I'll ask Professor Bailey.
Okay, thank you. So, first of all, I've enjoyed the manuscript. Maybe I didn't already told you. No, maybe in the report I mentioned that. So because it's very synthetic, comments on the results are clear. You focus on the most important thing. Also, I've already said that in some previous PhD events. I like the idea that the people doing eigenvalues are reusing their knowledge for solving graph problems, big data problems, etc. And this is very successful. In fact, you report on very impressive results and speed-ups compared to other methods. So it's a kind of stupid question, because I think I know the answer. But I mean, this is not what is implemented in the current libraries, solving these kind of problems. I'm using Vlov method, etc. This is anticipate that also this is not what is really used by Google, the kind of people. So they should jump on it, or people from NVIDIA should buy that immediately. So, I mean, you really expect that this type of technique will be implemented and used in the medical libraries very soon, right?
Absolutely. So actually it already is, because the spectral modularity clustering with Lanczos method and PageRank are already part of NDGraph, which is a library that is distributed with the CUDA toolkit. So it's about $2 million downloads per year. I wish it was in dollars. And so that's for the distribution of this work in particular. But I completely agree with what you said about the fact that spectral methods are not as used as much for this type of problem today, where we clearly have results showing that we should use more eigenvalue methods, especially when comparing against agglomerative scheme for clustering or other ranking techniques that Google use now. I think eigenvalue method and spectral methods for graph are very relevant. And yeah, we can do near real-time analysis of networks with millions of elements and find communities and important entities in those networks very, very quickly. So I hope we get a lot of adoption in the future.
In your presentations, maybe somewhere a few slides before, we report on the quality loss of your first implementation compared to Metis, if I remember well.
It's not Metis, so it's the same author. George Caritis is the author of Metis, and Metis is based on minimum balance cut. So it's a slightly different algorithm, but his recent work is actually on maximizing modularity, which is a more recent technique. And here we compare against his research paper that focuses on maximizing modularity.
Talk about, just curious, how do you measure the quality?
So here the metric is the modularity. So we look at how far we are from what we would expect randomly. So it's 0. So by mathematical property, it's 0 if we are close to random, and 1 if we are optimal. And here, I don't have the results here on this slide. I only show the relative quality, but it really depends on the network. But in this case, that's the modularity method. Another relevant one that would be to compare Metis against other methods is the minimum balance cut. Is the edge cut, sorry. And where the edge cut is just the number of edges that we cut between clusters. But yeah, in this case, it's
you mentioned something about the precision of computation that in some cases moving from 64 to 32 can be beneficial.
Yes.
Perhaps to go down to 16.
Yes.
8.
Well, that's challenging, but why not?
Even 16. Even 16.
Even 16, we're not sure, but I'm not saying we should do everything in 16, but probably we can. I'm quite confident we can do the SPMV in 16, and then we can keep the subspace into 32. Why not do the reduction in 32 as well, and just do the multiply in 16, which still, and storage in 16 would be beneficial, I think. So that would be mixed precision.
The last question, you mentioned a multi-GPU implementation, but well, you're solving clustering on the graph 1 billion in 2 seconds. You really multi-GPU? I mean, you have largest graph to deal with?
Yeah, so our idea at the beginning, we thought about multi-GPU a lot. And then we realized that we could handle graphs that are large enough in the GPU to cover like 99% of the use case. I know there are larger graphs, but there are very few of them. So that's why, yeah, it was not a priority during this thesis because of that. Because we just realized that we could solve most of the problem very quickly with having a very well optimized single GPU implementation.
Thank you. Professor Gaudieu, you can...
Thank you. I'd like to add my words of commendation for your presentation. I thought you did a very good job of going at the same time deep into your research as well as making it understandable to neophytes like me. So I'm quite impressed, and I'd like to commend you on this. I have a couple questions though. You started with a Twitter example and describing a graph. So it seems that a lot of the work that you've presented, it doesn't matter. A lot of the work you presented here implied that you were dealing with sparse systems.
Yes.
So where does it, would you estimate it breaks down? And how do you define sparsity, by the way?
Yeah, so sparsity here is relative to the context of graph analytics. So that would be the type of statistics that I showed at the beginning. So this is actually very sparse data and very unstructured and irregular data.
Yeah. My second and last question, I'm the sheep in wolf clothing here, or the other way around. I'm the computer architect here. Christmas is coming. What if Santa Claus gave you your wishes to design an architecture that would be fine-tuned to your problem? How would you change the architecture? What would you ask for?
That's a very good and tricky question. First, well, more bandwidth, of course. I would like more bandwidth. I would also like more DRAM, because it would allow to solve larger problems without going to multi-GPU. I'm confident that in the future we will have more DRAM. The problem is that the GPU memory is so expensive right now. That's why it's significantly smaller than the one we have on CPU. Those are, of course, obvious kind of answers. Also, everything that is related to load imbalance and supporting the CSR and CSR format is done in software right now. We could imagine some circuits to support sparsity and be better at doing sparsity also. So that would be more advanced optimization or architecture, but I think that would be very relevant to graph. That's what we all often see in FPGAs or this type of accelerators.
Yeah, that's what I was aiming at. Thank you.
Thank you.
So, during your PhD, you were not interested by multi-GPU. multi-GPU is very interesting for multiple subspace methods, but where the subspace are not nested. So
Yes.
I think for the answer of your questions, we can say also the multi-GPU or multi-node can
Yes.
be
That's right. That's right. Yes. So the idea is that we could benefit from replicating the problem also on multiple GPUs and with different parameters and just take the best result of the concurrent execution that we have. Yes.
Thank you. Dr. Eaton?
Good job. I enjoyed the talk. I'm familiar with a lot of this since I was involved with a lot of it. One thing I was unclear on was the error metric in choosing the subspace size.
Yes.
So there's a row function, which
Yes.
is some kind of distance metric. What exactly did you use?
It's there. So yes, let me come back to the slide. It will be more clear with the formula. It's here. So basically, when we have a subspace, we have multiple eigenpairs. So that would be those guys. Lambda is the eigenvalue, and the W here are the eigenvectors. For each one of them, we approximate the residual using Ritz estimate approximation of the residual. Then we take the maximum of all those eigenvectors. So we take the poorest approximation of the eigenvectors. That gives us the score for the subspace. And then we have many subspaces. So those are the Si. And then we just compare S1, S2, and so on. And here we take the smaller residual, which is the one that is better.
So yeah, so I was just asking about the definition of the...
Yeah, yes, you got confused by the max here.
Yeah.
So here we take we return as a metric for one subspace, we return the poorest approximation because we want to make sure we know that we may have very good approximation, but we really want to have good approximation for all eigenvectors. So that's why we take the max here.
The worst guy.
It's the worst guy, yes.
Okay.
And now that's why here we take the lowest because now we want the best one.
Yeah, that was the only thing that made me quirk an eyebrow. I didn't remember what was going on here.
Mm-hmm.
So good. The other question, I guess, is well, you mentioned there's only 1% overhead in the implicitly restarted Lanczos method
Yes.
because of overlapping, meaning you're able to do host calculation at the same time you're doing a GPU calculation.
Yes, because so let's say we are at iteration X, and at this point let's say it's a subspace size that we are interested in. So we will take this one and we will ship it to the CPU, compute the eigenvalue and eigenvector of this subspace, and at the same time the GPU can continue the factorization and continue the SPMV to compute the larger subspace. So at this point the CPU will end computing the eigenvalues, and now the GPU at the same time is computing the next nested subspace, which is larger.
Do you have some estimate of the communication required for this kind of...
Absolutely, yes. We just transfer the matrix and transfer back the result, which is the eigenpair. So the matrix is 4x4 to 20x20 in practice. It's super small. It doesn't even show up on a profile. Only a few dozens of an array of a few dozen of 32-bit or 64-bit elements.
Okay, very good. No more questions.
So, before asking for comments from your supervisor, I think I'll ask a few questions. First, I want to thank Professor Emad and for inviting me to be part of this committee. And I commend you indeed for your presentation, which was extremely clear. Now, okay, I'll come back to some questions by Professor Daly. So why doesn't Google use these methods, for and shouldn't this be kind of distributed? I mean, my question is why centralized may not be the right way of doing things.
Okay.
What do you say about this?
So there, actually, so yes, one and two questions in one. So why Google doesn't use that, right? That's very good question. Since they invented it, why don't they use it anymore? And actually, I think first their graph now is huge. It's the graph of the World Wide Web. We could solve eigenvalue problem on that for sure. But the thing is that I think they also changed all their infrastructure, and it now makes, like with Hadoop type of thing, which makes it possible to run linear algebra on it, but it's far from optimal. And I think at some point they realized they had advantages to move to a vertex-centric type of programming. So instead of solving the eigenvalue problem, they just try to propagate the influence of vertices by sending messages to their neighbors. That's one thing, and I think there is also another more business reason, is that people quickly understood how PageRank was working, and they started to try to trick it. So they had, over the year, they had to add more and more metrics. As far as I know now, they have more than 30 metrics when they combine together. So I think PageRank, the original PageRank, is still one of the metrics they use. And I'm not 100% sure if they use spectral technique or not. I would say on Hadoop, I'm pretty sure they use Hadoop, and I don't think they run a spectral method on Hadoop, or at least I wouldn't.
I have a question now also about the quality loss, when you use for spectral modularity maximization. The question is that I looked at your tables of results, okay?
Yes.
And I saw that you had better quality on small examples.
Yes.
As soon as you got to larger examples, you had was quite fairly systematic. So maybe in the formulation there is something which makes it that structurally there is a difficulty, okay? And because you state in your document, well, I'd like to have vectors with zeros and ones, selecting, and then you go into eigenvectors which don't have such structure, okay? And so shouldn't you ask, or somebody would like to have better quality, ask for some kind of sparsity in the vectors? Can it constrain kind of eigenvalue problems, sparsity constraint, something like that? So
yes.
Okay.
So So first about the quality, we can. I think you're talking about the quality without Jacquard. We can catch up a little bit with Jacquard. But there are actually many things that can go wrong, and many reasons why quality is lower. The first one is that we have the k-mean to come back from this discrete problem to the floating point value into the discrete cluster ascent. This is completely empirical. We just found that it worked we didn't, someone else found that, it was Newman who did that, found that it works in practice, and that's why we are using that right now. There is no guarantee or proof that it's the best way of doing it. Also, usually in CPU partitioner or clustering techniques, there is the refinement step. So here we just return the raw results without doing any post-processing. Usually they run some kind of something called Kernighan mean algorithm, and they will look at the frontier of the cluster and try to swap vertices from one cluster to another to see if that maximizes the metric or not. So that will basically improve the boundary. And we could also constrain the eigenvalue problem directly to try to make it better for them. One last thing is regarding the size and why on small sizes we are better than on large sizes. And we actually did systematically agglomerative scheme on small sizes. That's because of, I believe, the method in itself. Like for the spectral technique, we have a global approach. So basically, we solve this global maximization problem. So we capture things that are more visible at the global scale. while for the agglomerative technique, it's a bottom-up approach. So we are better at seeing things that are visible at the small scale and then gather stuff. And I think that the bottom-up approach may be naturally better when the graph is large and we don't apply any type of pre-processing and any type of constraints into the enforcement. That's fine.
Okay. Then I think there's a comment. It's about the overlapping when you talk about the acceleration of Miran.
Mm-hmm.
And what I would like to see, but it's a comment. It's to visualize this overlapping. How much overlapping there is between what you have in green and what you have in blue in those slides. The eigenvalues solver.
That's right here.
34. But
the overlapping happens here.
Uh-huh.
I mean, all this part is overlapped with this part.
Okay, so it's shorter. It takes less time than on the factorization.
I mean, from the beginning, it was not taking that much time, but it was just it's just task parallelism. Those are two tasks that are independent. So there was no reason not to overlap it, even if it was not huge from the beginning. And I wanted to overlap it too because I wanted to show that the auto-tuning was basically free in this case. When running on accelerators, we could overlap what the accelerator does with what the CPU does, which is a big difference. That is something you cannot do if you only run it on CPU.
Very small question, just by curiosity. You talk about using prime numbers for clustering at some point, rather than powers of 2, I guess.
Yes.
Why is that?
Yes, that's very interesting, and that's because the way finding multiple cluster was done in the past with spectral clustering was done by solving recursive dissection problems. So basically what they would do is they would compute the largest eigenvector and split the cluster in two, and then each subcluster they will recompute everything and get the eigenvector for each cluster and split it in two again and so on. So by doing this kind of recursive dissection, they couldn't find the 3 cluster example that I showed, for example. That's why I used 3 in this example, and that's why in all the performance results in the physics, I often select 7, and that is because that highlights the contribution of our solver.
The others can't do it. Okay, well, thank you very much. So,
thank you
for comments, maybe for Emma.
Just a question about your perspective. Do you know can you connect machine learning and the multiple restarted coder from subspace method? Do you have some information to give to machine learning as input and output?
Well, it's almost already machine learning or artificial intelligence. Usually, clustering is part of artificial intelligence and machine learning applications. So we are that actually, for example, spectral modularity maximization is one way of integrating multiple implicitly resorted lengths into AI and so on. But I guess you had something else in mind. If I'm correct, you're maybe thinking about using machine learning for parameter auto-tuning, right? Okay. So for parameter auto-tuning, well, we could use something smarter, more adaptive. For instance, right now even with the frequency, we generate subspace at a regular strides. While in the future we could have something more adaptative that would detect where the subspace size tends to be better and maybe try to select subspace sizes that are closer to this size for the next restart cycles, for example. And that would be not only auto-tuning of the subspace size, but kind of intelligent auto-tuning of the auto-tuning itself.
Good answer. And you know, you can add also the restarting the strategies and many other parameters.
Yes, yes. Here we focused on auto-tuning of the subspace size. There are plenty of other parameters. Like, for example, the input is random here. There are plenty of work already on improving the random guess of eigensolvers, and you can imagine some intelligent strategy here too. And
okay, thank you. You know, evidently I haven't questions, but I would like to do a comment about Alexandre. He did a BS degree in computer science and MS degree in high performance computing, and so he didn't know many things in numerical computation. But I would like to insist that he can be considered now as an expert in high-scale eigenvalue computation. I am very happy to say that you are very good in for the comprehension of very difficult numerical methods as IRM and so on, integral methods. And really, I think it's you did a very good work. I am happy to do this work with you.
me too.
I am proud of you, and so thank you.
Thank you so much.
So I 100% agree with Nate. It was great to work with you during me for last year, and I hope to be able to still do good research with you on the next year. So it's why I don't have really question. I already asked you a lot of questions. I will just have some questions, but for the future on from perspective. I wanted to ask you about learning for auto-tuning, but it's one I think of the interesting question to work on the future. I also think that cluster of GPU is very important because, of course, these days we don't have so large network, but the coming year we'll have larger and larger network, and it will be very important to be able to use this cluster of GPU. So I will have two small remark questions. So one is about, you spoke about Hadoop. So I know that now even Google sometimes use MapReduce for the sparse matrix vector multiplication. So there are more and more people doing linear algebra using MapReduce. So do you think, I'm not sure at all, but for Jacquard, for example, do you think it's possible to use MapReduce or this kind of tool? I'm not sure at all.
I'm not sure. So, well, we can formulate Jacquard as a matrix multiply, and we could do a matrix multiply with Hadoop. I don't think it's going to be optimal, but that would be a way.
To compute the intersection, the union of sets using this kind of...
I think we can do it, yes.
Perhaps it will not be so efficient, but you can like this address big data applications here.
Yes, yes.
It can be interesting.
Yes. It's about, after all, Jacquard is about computing intersections of arrays and union of arrays. So Hadoop should be able to.
And another question for the future. So now you are using GPU, and but more and more on the future, and it's always the case for the top one supercomputer, you will not have any more shared memory for all cores. So if you assume that you don't have any shared memory on the accelerator, what kind of problem you will have to address?
Yes, so we already addressed it a little bit on GPU, because even if there are shared memory on GPU, it's actually what we call shared memory is only shared between 32 threads. It's shared between a warp. So it's not shared between all of the 5,000 cores of the GPU. And we already have adapted our strategy to that. So, for example, when the first example that comes in mind is for small sparse matrix multiplication. We usually we replicate the small vector into shared memory, and then we have all the random accesses into shared memory by replicating this vector for each training multiprocessor. So that would be a way. I don't think, well, if at some point there is no shared memory or cache at all, we would have to go to algorithm, I think, that are closer to vertex-centric algorithm, clearly define what is the role of each core and who sends what to whom, and how the communication operates between those independent cores that will not have shared memory anymore.
Anyway, so I hope to have the opportunity in the future to work with you on a cluster of accelerators with no shared memory.
Me too.
Okay.
Thank you.
I'll turn to the audience. Maybe someone with a PhD in this room would like to ask a question. So you, one? Okay. So then I ask you to leave the room because the committee will deliberate in this room.